In this penultimate instalment of the series on infinite Archimedean polyhedra, I'll be covering a small selection of the remaining figures. In order to find the truest infinite cousins to the 13 classical Archimedean solids, I've imposed these conditions. Every face must be a convex regular polygon. It must be vertex transitive, every corner looks identical. It must be triply periodic, extending infinitely in all directions. Flat edges are excluded. And it must be acoptic, intersecting faces are not allowed. This is one of the few infinite Archimedeans that contain octagons. It takes the form of layers of octagonal prisms joined square to square. Each layer is offset from the layers above and below. Like all of these objects, the surface divides space into two intertwined regions. Sometimes these two regions are the same shape, but usually, as in this case, they are different. If we journey inside one of the octagonal prisms, we enter a series of octagonal chambers joined by square portals. But travel into the spaces between the prisms, and the view is very different. We have a series of great rhombicube octahedra connected by hexagonal portals. If you view this object as a surface, these are just the two sides of the surface. But it's equally valid to view it as a solid object, in which case you can either see the octagonal prisms as the solid, or their so-called complement, the great rhombicube octahedra, 2 for the price of 1. This next one can be neatly constructed from 4 sets of partial tessellations. Starting with layers of hexagons, if we add 3 sets of square tessellations, we end up with this shape. This has a distinctive layered appearance. If you were to journey into one of the layers, you'd see a floor made of hexagons, with triangular tubes connecting to alternate layers, like a lift that services only the even-numbered floors. Meanwhile, triangular columns hide the lift shafts between the odd-numbered floors. This is another one built on great rhombicube octahedra. One side of the surface is rhombicube octahedra, the other side is truncated cubes and truncated tetrahedra. This shows that a combination of these shapes fills space precisely. This type of structure is called a honeycomb. All of the infinite Archimedeans are simply honeycombs with some faces removed. This particular one is a uniform honeycomb, as all of its components are uniform. I hope to cover honeycombs in a future series. We've seen that the vertex configuration doesn't fully define these figures. For example, 6 squares meeting at a vertex could be a mu cube, or this Wells figure, or a twisted mu cube, or even a squashed mu cube. They're distinguished by the full vertex figure showing the angles between the faces. However, the next 2 figures show that even the vertex figure doesn't necessarily pin down the object. These 2 objects are both 3, 3, 3, 4, 3, 4. And surprisingly, they have identical vertex figures, despite looking very different. On the left is a dense figure, hard to decipher at first sight, but the object on the right is quite open, like one of the crystals grown in the previous episode, with a cube octahedron as a seed, and 4 octahedral branches growing out of it. The reason for the difference is the way adjacent vertices fit together. On the left, adjacent vertices join in such a way as to twist the figure towards itself, leading to a dense figure, whereas on the right, they join like edge to like edge, making for a more open structure. The only other pair like this I know of is Wells 465T and the twisted mu cube with a twist of precisely 15 degrees, which share this vertex figure. As a final example, this object has 8 faces adjoining each vertex, including 4 squares. I suspect this is the maximum number possible unless all faces are triangles. The vertex figure is a classic saddle shape with rotoreflectional symmetry. There are many more infinite Archimedeans I haven't shown. I've included my references in the description for those who wish to dig deeper. This remains a little explored frontier, and I've no doubt there are many more waiting to be discovered. The series isn't quite over just yet, however. In the final episode, I'll be relaxing the rules, exploring what happens when we soften our constraints to uncover broader families of infinite polyhedra. Thank you for watching. If you've enjoyed this look into the rest of the infinite Archimedeans, please do leave a like, and see you in the next video.